Hello all, and welcome to your first lesson of this week. And we're going to talk about volume this entire week. So this is broken up into 3 lessons, and we're going to start with discs and washers, looking at Chapter 6, Section 2. So get yourself ready for notes, and we're going to get started. What may be familiar is if we're looking at this image here, when we talk about a revolved figure and its volume, we're taking an area under the curve, or perhaps an area between curves, and we will rotate it around various lines. There are definitely ways to do it around slanted lines, but we're going to focus on vertical and horizontal. So in this case, you can see that we have a function that is then being revolved around the x-axis, because this is the center of our revolved figure, and so that's how you can tell which line it's being revolved around. Now, one way that I find it helpful to think about is here is a very small little Riemann rectangle. It's got a length here, which is just our tiny little dx, right? It's a tiny change in x. And then its height is y, right? Because it comes all the way up to the top of the curve. Now, in terms of the volume, when I take that single rectangle and I rotate it around, it creates a disc, which is the same as like a little cylinder. So it's looking like this. It's flat on top. It would go back behind this here if we could see it. And if we're just looking at that single flat cylinder, that's how we get this formula, which is pi r squared h. If I'm looking at this picture, the height of this tiny little one here is still our dx, right? Because it's this distance. And then the radius from the center here is our y. So that's when I can do some substitution here. And instead of pi r squared h of that little thin, in this case purple rectangle, that's pi f of x squared dx. Because I'm just substituting in for r and h. So then if I want to find the volume of the entire figure, I want to add up all those little rectangles, the one here, 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 and so on. And I'm going to use the integral to add up a Riemann sum, pretty traditional, from a to b, which are our bounds on the x-axis, of pi f of x squared dx. So that's where that formula comes from, and that's what I always like to fall back on. I will tend to always draw a picture of the rotated disc or washer, or if it's a cross section or a shell, which we'll talk about in later lessons. I tend to always draw that picture, and if you're stuck, I recommend that you also draw them as well. So in number 1, it says write the integral to find the volume created when the region R enclosed by the curves y equals x and y equals x squared is rotated around the x-axis. So as I said, I'm going to start with a picture, and I know that this is my line, y equals x, and then my parabola here, which is y equals x squared, and my region that I'm rotating is then this small little half circle moon shape right there. Now, as I said, I'm going to use the same method that we saw in this picture here. So I'm going to just consider a small little Riemann square being rotated around the x-axis. And this is what's going to create a disc, because there's a gap here where it rotates around. And I can even draw that a little bit bigger, because what happens is that the x-axis goes through the center, and then the difference is then just this difference here in between the two heights. And then it still has a height dx, and this creates what's called a washer, because it looks like the thing in a hardware store that's called a washer. It's not a very creative name. So when I find the volume of this small shape, it would be the big radius, which we'll often see written like this, which would be, this is big R, That would be the full disk minus the little one, which would be this smaller r here. Now, since they are defined by functions, this upper one being defined by y equals x based on the picture. So in the case of this function, that would be volume is equal to pi x squared, because that's big R, minus pi, and then the smaller radius here is y equals x squared. So we are going to square that again because we're looking at the squares from here, and then this is the square from the formula. And then this whole thing is multiplied by height, because that's the same for both, which in this case is dx, because we're looking at a small rectangle around the x-axis. So then the whole thing is the integral from a to b of pi x squared minus pi x to the fourth dx, and you could do some simplification if you want. All I need now is to find a and b, which are the points of the intersection, similar to what we talked about last week, which you can do some algebra where you can say, oh, well, when is x equal to x squared? Or you can use your mathematical knowledge and say, oh, that's 0 and 1, factor out a pi, x squared minus x to the fourth dx. And that would be a fine volume integral, because it doesn't say evaluate, of this. Hopefully, those are both polynomials. You would feel confident evaluating that. Now, one thing that you'll often run into is where you're dealing with not around the x-axis, but a different line. So in number 2, we're going to talk about that same space, but being rotated around the line y equals -1. So again, I'll draw my picture very quickly. I'm going to zoom in a little bit more. We've got our region here from 0 to 1. And now, though, we're rotating it around this line here. This is going to be our new center, which is y equals -1. So again, I'm going to think about our rectangle. And when I rotate it, because we're going around a farther away line, the radii are much bigger. So it's a much larger washer, but there's still a lot of more space in the middle. But I'm going to use the same basic idea where we have our large R, and then we have a smaller one to the lower bound. So we're going to come from the same formula of pi r squared minus pi little r squared, in this case times h, which is again dx, because that is the height here. Now, large R squared is going to go here, which is one space, because we're in between 0 and -1, plus this extra to here, which is x. So big R is equal to 1 plus x. Little r, by the same note, is equal to 1 plus x squared. So when we plug that into our formula, we end up with pi, and make sure you're using your parentheses here, 1 plus x squared minus pi times 1 plus x squared squared, and then again times dx. So our final integral, and again, you can simplify it farther if you want. I'm going to just factor out the pi, 1 plus x all squared minus 1 plus x squared squared dx. And this is why the picture is really helpful for me. If it's not helpful for you, that's fine. I understand it gets a little messy. If you want to see a slightly neater one, I recommend that you look at the PDF attached. And then, of course, if we're rotating around a horizontal line, we're using our dx. Just as a thought, if we're rotating around a vertical line, this is what the rectangle would look like as it goes around like this. And this distance is a change in y. So just be thoughtful. You're still using the same method. It's just a horizontal versus vertical disc or washer. If you have any questions, nominate them in the form or leave me a comment, and I'll talk to you later.